afternoon, and welcome to the latest Fluid Power World Technology webinar. I'm Rachel Piscini, Senior Editor of Fluid Power World. I'd like to thank you all for attending this talk on integrated systems and how they are key to profitable sustainability. We'd like to thank our presenters, Howard Zhang, PhD, and Rich Nagel, for being here today, and special thanks to Parker Hannifin for sponsoring this content. Before we begin, let's go over a bit of housekeeping information for the ON24 system so that you can participate in today's discussion. On the console, you'll see a number of boxes which you can move and resize to suit your preference. If you need technical assistance, use the Help widget at the bottom of your screen or use the Q&A widget to contact us directly. If you have questions for the presenter, please type them into the Q&A widget. We'll be answering all questions at the end of this presentation. Thanks again to Parker Hannifin for sponsoring this webinar. Now I'd like to introduce you to today's presenters, Howard Zhang, PhD, and Rich Nagel. Dr. Zhang is a Chief Engineer and Parker Engineer Fellow for Parker Motion Systems Group with over 20 years of motion control industry experience. His current focus is advancing Parker's engineering innovations and intelligent mobile hydraulic system controls with power-dense and efficient ePumps. Rich Nagel has more than 30 years of experience in motion and control industries, having served in various roles of field sales and applications, product management, operations, and global business development. He joined Parker's new electrification growth team in April 2022. We are so grateful to have you both here today, Howard and Rich. I'm going to turn the microphone over to you so we can get started.
All right, well, thank you. And I'll take the lead. Well, thanks everybody for attending. So Howard and I both live in the kind of crossroads of hydraulics with a lot of hydraulic background between the two of us and also controls. Howard primarily mobile and mine prior to this job, a lot of industrial, but yeah, we are all trying to figure out electrification and what that means for our industry. And so today we're going to talk a little bit about integrated systems and how they can play a role in helping build more efficient machines, which is really one of our primary goals here at Parker. So some of the topics for today, just general market trends, requirements for fluid power systems. And when we talk about fluid power systems, increasingly, the integration of control systems and electromechanical capabilities with traditional fluid power. And then very important for e-mobility is maximizing power density, and in this case, the hydraulic system, to minimize the battery consumption and to maximize operating life. The benefits and some challenges of integrated components for electrically operated equipment, which is a little different than your traditional just bolt together systems. Some of the methods that can be used to reduce installation and overall maintenance and operating costs. We'll talk a little bit about thermal management elements in these types of systems and why they're critical to the component life cycle. And then lastly, all the different technological advances going on, both in connectivity that lead to better machine productivity, reliability, and also maintenance. And there are just so many things going on right now. I'm not sure anybody in our industry completely has a full view. We are learning every day. So thank you for joining and helping us through this journey too. So of course, when we talk about electrification, any discussion on electrification kind of starts with batteries. Parker's not a battery supplier. We are building our expertise, but the way we frame this, right, is that in the world of diesel engines or plugging into the wall, right, to run your hydraulic system, we took a lot of things for granted. Number one, availability of diesel fuel, for example, and very high power density that you get from diesel fuel. So a very relatively small amount of fuel, both weight and envelope, can provide a lot of power density. And to try to replicate that with a battery, I think we all know, right? We get a very large, very heavy device that requires time to charge. So for example, we all know you can fill your truck up in a couple of minutes, and with a 240 volt charger, it's going to take a couple hours to fill a battery that's suitable for this equipment. So what that means, from our viewpoint, is that since the hydraulic system along with the propulsion are really the two main uses of the battery power. That system efficiency now becomes really critical. And for most of us who grew up in hydraulics, we didn't really worry a lot about efficiency. We threw a bigger heat exchanger on, or we accepted pressure drop to get better control. And we have to look at our systems differently now. And we'll talk a little bit about some of the system architecture and how we get there. And Howard's going to go into a little bit of a deep dive on that. So, of course, where we're all at today with electrification is we've got these market drivers, and of course, there's a cost reality, and then there's a performance reality. And we all understand the performance of diesel-driven systems and the cost side because it's very established. And when we look at the four drivers, the things that we're trying to manage, of course, our overall system efficiency, and then really power density, that's both on the electronic side and the hydraulic side, the thermal management that's required. And remember, thermal management here is about dealing with inefficiency. So, in the world of batteries, any inefficiency means a lost opportunity to use that battery power. And so thermal management is not just the cooling loop, it's reducing the need for the cooling. And then lastly, we talk a lot in our hydraulic kind of overviews here, when you get rid of the diesel engine, the hydraulic pump becomes the noisiest thing. So how do we mitigate that? How do we balance efficiency versus noise? We'll talk a lot about that. When I kind of chart this off, efficiency versus cost of ownership, and that's acquisition cost, operating maintenance. We look at diesel machines, relatively low cost of ownership because they're very mature, right? We have all the service models in place. Efficiency is relatively low, and that's not just the diesel engine, but the hydraulic systems that are typically attached. We look at today's electric machines, and that's that red dot up in the upper right corner. Fairly efficient. The motors themselves are extremely efficient. Inverters are very efficient, but the hydraulics still have a ways to go. And of course, very high cost. And then, we move towards this green dot kind of in the center, which is really the point where these markets can grow profitably, fleets can make money, municipalities can operate their equipment efficiently. And of course, we're going to need higher efficiencies to reduce that total cost of ownership. So, from the diesel standpoint, we've done a lot of what we can. And the only way to really move up the efficiency curve is through electrification. And then, of course, to get the cost points of electrified machines lower, it requires a couple of things. Innovation, which is where these integrated products play into, and really more manufacturing scale. And so one thing you'll find with these integrated products, they do require a certain amount of scale. They're not piecemeal like typical hydraulic systems where you can take out a valve and put in another one. They are a little bit more on the automotive side where you require a certain level of scale to get the cost down. But that's where we're going to have to go as an industry to make this equation work. So when we talk about fluid power technologies, for the folks here who have a hydraulic background, I think we have a pretty good understanding about the potentials and benefits of fluid power technology. In electrification specifically, we are helping to support, carbon-free, carbon-reduced policies, local and regional emission regulations, which of course they vary all over the world and all over North America. We're seeing, lower noise regulations, especially in big cities and driven by municipalities. And once again, not just in a requirement than for smaller, faster, and more efficient hydraulic products and electromechanical products that are part of the overall system. Of course, some of the challenges we like to tell people all the time, just getting rid of the diesel engine and replacing it with electric motor doesn't solve all the challenges. It creates some different challenges, and we'll talk a little bit about that. A lot of our existing hydraulic products that have worked just fine for years in traditional mobile environments are not going to work or be ideal for future electrification. We'll talk a little bit about that. And then once again, the thermal management of the systems and reducing inefficiencies key. And then lastly, some of the potentials. So this opens up really the design playbook for higher speed, more power dense hydraulic products that utilize new designs and absolutely more automation in the manufacturing side. Modular integrated products that are more cost effective with manufacturing scale. So that's the supply chain and the automation assembly process. And then of course, digital, right? That just kind of permeates everything we do today. Having connected products, how does that improve efficiency, productivity, and of course, very importantly is safety. So we won't talk a lot about safety, but that's kind of the underpinning of a lot of what we do for electrification with hydraulics. So why electrification? Why now? Big hot button topic for a couple of years. Anybody's been to ConExpo or BAMA, you see electrification everywhere. Shows are sold out, ACT shows. So, number one driver, we have customer demands. And at the end of the day, we have to provide reliable solutions for fleets and municipalities so they can make money, because ultimately they have to operate this equipment in a way that is profitable long-term. The other customer demands are extended battery operation. We're not battery people, but we produce the products that consume a lot of the power from the battery. So it's important that we have efficient products. Charging infrastructure in remote locations, construction sites, that's a huge customer demand, kind of beyond the scope of what we're talking about here. And of course, there's just changing attitudes about EVs, both good and bad, as people become more experienced, see what they can do and see what they can't do. Of course, on the regulatory side, we have a lot of government carrot and stick programs, right? Incentives and disincentives. We see a lot of regional differences, state to state. And then, of course, globally, as our industries are very global at this point, we see a lot of direction from Asia, Europe, that find their way to North America, and we're trying to find a place of equilibrium. And then technologically, a lot of it is in the electronic side and controls. Power electronics become denser, higher voltages, higher current capacities, a lot more computing power everywhere, connectivity and data, IoT cloud solutions, autonomous operations, which is kind of beyond our scope, but part of electrification. The IoT solutions with over-the-air software, right? So that we can not only pull information, but push, and just more by-wire solutions, whether that's just operating a boom, a brake system, or a steering system. We're seeing more and more, decoupling from cables and just pumps and valves, but using control systems. So, some of our challenges for hydraulic systems are pretty clear. The number one, I wouldn't say the number one, but maybe one of the top issues we see here is our pumps today were designed for traditional diesel applications or power takeoffs or industrial, and RPMs were not the problem. Generally, we could go up to 2,500 or maybe 3,500, and that was fine for most hydraulic system engineers. But when you look at the motors that we have available today for electrification, they're operating in the sweet spot of 8,000 RPM and higher. And so we have a mismatch. And of course, longevity, the way we operate pumps and electrified systems is different than we see in diesel. So there are longevity concerns. And of course, all the normal hydraulic concerns, leaks, cooling, getting good diagnostics. Another side of this is, when we run the pump at higher speeds, we have to be concerned with cavitation and inlet conditions. And then we have a lot of unique conditions in electrification governed by a lot of different ISO requirements, but also good hydraulic practice. So safety is always paramount in system design. And then I'm going to turn this over. Howard, you want to take the integrated ePump?
Okay, great. Good morning. Thank you very much, Rich, and good morning, everybody. And thank you for attending this webinar. And Rich has presented an overview of a market driver and the electrification challenge for, say, fluid power products, including components and systems. Now, let's see how integrated ePump, like a pump and a motor pair, could help solving those challenges. You can, on the right-hand side, this is a integrated ePump. We call it like a fully integrated. And you will see what's inside there, but it's actually a pump, hydraulic pump, electrical motor, and the controller or inverter put together in one package. And by doing that, you would you would have an advantage if you design correctly. You would have a higher efficiency, and more importantly, is a plug and play and safer and plug and play. If you do that right, it can also improve the reduce the noise and simplify the structure and reduce the footprint definitely, and reduce the cost even. People will say, okay, well, how? But we will explain how. That the main market segment we are trying to use this thing or apply this is on a work truck, a heavy-duty truck, and the mini construction. You can see all those little icons at the bottom. So what is the integrated pump and how it's been put together? You can see from this picture, we have on the left-hand side are the inverters or controllers. On the middle, at the middle is actually the motor. Motor basically is just like the key components, the rotor, stator, and house. On the right-hand side, it's actually a fully integrated hydraulic pumps. And it can be different pumps there actually. So that's the structure. With that, this is a comparison of integrated ePump, so motor and the pump pair, we call it ePump, compare with the traditional induction motor plus a pump bolted on. Those are the real numbers, like with the same horsepower, same working condition. You can see on the top one is actually much bigger, and the lower one, the bottom one is integrated. It's very compact and light, so power density is much higher than the top one. And we actually have a reduced bill of material. The reason for that is the cables. We don't have those cables and the connectors, external hydraulic hoses, all this thing. We try to put that internal. This is a prototype. You have the cooling hose outside, but the production part is actually built in. And the other major benefit is for OEM, is a flexibility. They can put this thing anywhere they want, rather than just put it on a particular space with a special mounting. And also, it's actually easy to use. It's auto-configured and auto-tuned, so no tune is required on site. And if you design it properly, it's actually quiet. We proved that can be done. It's actually quieter than when you bolt this big motor and the pump together. And so that's the benefit. That's the simple benefit. And the other part we're going to talk is the mismatch Rich just mentioned between hydraulic pump and electrical motor. You can see from this graph, the vertical axis is a torque, input torque, or pressure in hydraulic term, and the horizontal line or axis is the speed, operating speed. You can see for a normal, like existing hydraulic pump, their peak efficiency region in this example is between 1200 RPM to 2700 RPM. And the efficiency actually is pretty good. It's pretty good in terms of hydraulic pump. But however, if you look at the electrical motor on the right-hand side, the most efficient range or operating range is actually beyond what is actually double or more, beyond the hydraulic pump operating range. So this one is 3,400 RPM to almost like 6,000 RPM. So there's a mismatch. To solve that, a smaller and a faster pump technology or improvement need to be done and combined with this high-speed motor, electric motor, that can definitely increase the total unit power density. And in the same time, if you move the efficiency range of the pump towards the higher speed, then you can optimize this ePump efficiency. So that's another benefit. Okay. This can be further illustrated by this generic graph. You can see it here, the solid line is hydraulic pump. The torque, continuous torque or pressure, hydraulic pressure, and the horizontal line is also a speed. You can see hydraulic pump, they are very high torque, but their operating range or speed range is actually is low. Actually, in this case, it's a 3,000 RPM or less. So that's the regular operating range for hydraulic pumps. But a different story for the electrical motor. They actually, most efficiency point is beyond 3,000, 4,000 to 6,000, as the last example showed. And they can run at much higher speed. So to match hydraulic pump with a motor, we need to do something. One is use smaller and faster pump and integrate it with the motor to increase the power density. And if you do that right, it also increases the efficiency. The other one is people can say, okay, you can use gear. Sure, you can, but it will with added inefficiency and also the cost. So we talked about how we can increase the power density of this ePump and what that will do to the efficiency of the total unit. And to improve efficiency of the system, reduce the battery size or reduce or make the battery run longer, the improvement on component only will not do the job. We need to take that in the total system point of view. And the total system, the hydraulic system was normally classified in 3 categories. One is the centralized architecture, as shown on the left. So you have just like the current diesel engine. You drop the engine, put the big electrical motor, replace the engine, and have hydraulic system and actuation kept the same. That's one. Or you have a decentralized architecture where you still have the little smaller, but still big hydraulic pump and with a electrical motor. And another portion, you can separate the function of 1 function or 2 function, depending on your application. So you separate it, and this is decentralized architecture. The third one is distributed architecture. I just call that the future state. And we will talk about the advantage and disadvantage of each in the next couple of slides. As we see, the centralized system architecture is you have a battery, and battery has a power. You have an inverter and the electrical motor. Big electrical motor drives single pump. In this case, I actually use a gear pump as an example because your motor can do a speed, like a varying speed, varying the flow, but you can also use a variable pump here. I just use the fixed pump as an example. But all the actuation is like a speed of the actuation or implement is regulated by the centralized valve. They call it valve bank. And the good part is it actually you can maintain all the hydraulic portion untouched. So that's a good part. But from this top picture, you can see it's a very inefficient. You have 55% of valve loss, the total loss, 55% of the input power being lost or wasted by the valve throttling. And again, your motor and pump loss is also significant. You only have, in this case, 10% of your energy to do the work. So you can see the battery will have a hard time, your system will have a hard time to maintain the temperature, or they have a thermal issue. And the next one is a decentralized, we call that a transition state. So you can see on this system, you have a motor drive a pump. In this case, I use the variable pump. The other path is use the pump together with the motor, high efficiency pump and motor drive one function. So that's decentralized. And you can see the efficiency over the centralized system is actually quadrupled. It's a big difference. So by doing this, you definitely will save a lot of energy, like battery energy. But still, you couldn't get the full benefit of this pump and motor pair. And you still have a valve throttling loss, and you still have the idling loss, partial idling loss. The future system architecture, or the architecture that mostly fitted for electrification, is this distributed electrical system architecture, because the pump and motor pair, it's very flexible, as I mentioned. You can put this anywhere. And the benefit is you have a fully distributed system, which you actually have maximized the system efficiency. The good part is you have a dedicated pump motor pair, and you allow maximize system efficiency, and you have a full power on demand with no throttling. So if one function does not need the power, you just basically turn it off. And a disadvantage could be your architecture is simpler. You can see it less like a mass, but your component and the system complexity is actually increased. And you also need a coordinated, synchronized control for the total system. And it also requires a smaller, faster, much more power dense ePumps to avoid excessive installed power over your the total power. So this this one is actually a summary of the three system architecture comparison. You can see the red one is the centralized system. The middle, the yellow, is the decentralized, and the green is the distributed. So this the efficiency comparison of three. And you can see I'm not going to read the advantage of this distributed system architecture. You can see it here. The other important part I need to mention is by doing that, you actually optimize the thermal management. And by optimize thermal, you actually will have a much less, like a cooling need, and also your HVAC system can be quiet, or sometimes like not use it. Yeah, so that's extra benefit. So when we talk about this efficiency, how that efficiency will affect other part of the electrification, because the other important factor is a noise. But why noise? Why we say we have this noise issue or noise problem now, not before. It's all because you have this big boy there, stay there for a long time, and that big boy masked all, if not all, is most of the hydraulic noise until your diesel engine phasing out. Now your hydraulic product, a hydraulic pump, is at the forefront of the machine operating noise. Everybody knows, oh, your hydraulic pump is noisy. Why they don't see that before? Because there's big engine, much noisier than the hydraulic pump. We will show that in the next page. But how important is a noise, or actually no noise? How important is a low noise? It's really depending on the market and depending on application environment. For markets or applications that do have a high priority towards the noise mitigation and reduction, there are a few thoughts to reduce it. So where did that noise come from? The noise is actually depending on the pump technology, system technology, operating condition, and definitely the pump speed and pressure, and also the mounting, like how does the pump and motor mount to the machine. Okay, and so here is a generic picture of the noise distribution or noise chart for a variety of pumps. You can see this is like a generic picture. You can see the lowest noise pump on the left-hand side and the highest noise pump on the right-hand side. Definitely is still lower than the diesel engine, but the Bantex pump is the highest, has the highest noise. But again, this noise is not the single factor. The noise and the efficiency, sometimes they have trade-offs. The highest noise pump in this case, you can see from this graph, has the highest efficiency. So depending on your trade-off, you can pick the lowest noise pump or highest noise pump or highest efficiency pump. So there's a trade-off. But this is not the end of the noise and the efficiency story. People are actually, like all the manufacturing, are developing new technologies to deal with the noise issue, but still try to maintain the high efficiency of a hydraulic fluid power product. There are a lot of new development going on, actually. That one is actually, for electrification, that's a very good thing. So then then I'll hand over to Rich again to talk about
all right. Thanks, Howard. So obviously, one of the takeaway here, not just really the product concept of an integrated ePump, it's really about a distributed hydraulic system. And it's not something we could do in the past, but now with the ability to have motors and drives integrated with pumps, we can actually do this and are doing this on machines here. So one of the takeaways is really what do we get out of these distributed systems? Obviously, efficiency is paramount here with any electrified machine. We can turn this off when the function is not required, so the noise goes away, parasitic hydraulic losses go away, and we're not drawing down from the battery. Ease of maintenance. So essentially, there is, and we'll talk a little bit about data that comes out of the device, but these types of devices are not things that you necessarily try to troubleshoot and repair in the field. It typically is something that you replace, and you've got the tools to tell you really what's going on based on the data. And so obviously the other outcome of being able to turn off and better efficiency is less battery drain. That's probably key, because the battery is such a huge cost here. And then we can really optimize these systems to create an ideal operating condition, because we can tailor the integrated ePump capability for the actual function on the machine, which we couldn't do before. Most of the tuning was done on the valve, and the valves give great control, but they're also, they're generate a lot of heat, right? And they're pretty big wasters of energy. So talk a little bit about thermal management, right? And so what we do with thermal management on these integrated pumps, we design a lot of the efficiency into the product side. So, one of the questions is, where do we get cooling from? Well, typically it's a hydraulic system, and on a lot of construction equipment, the preference is to use the hydraulic loop to cool the device. And of course, there's typically a heat exchanger somewhere on the system, right? And in this case, if we're distributed, we don't have a centralized heat exchanger. By having distributed ePumps like this, we do get a fair amount of convection cooling. And you can see this animation in the bottom left. It shows the convection capability, how the heat is displaced from the housing, right? And so by having all that surface area distributed around the machine, we get typically pretty good airflow and pretty good convection. And so, a combination of convection and hydraulic cooling is typically what we use here. So the con is, we do have then, you got distributed products, so you have some duplication of cooling loops potentially. The other thing is oil cooling is generally about 15% less efficient than water glycol. And of course, if you're going to have a battery and inverter, you're going to have a water glycol system to cool that. It's absolutely required. Well, I mean, you can run it through hydraulics too, but typically not as efficient. So it really depends on the machine design. At the end of the day, though, having less inefficiency in the system allows you to have less cooling overall. So generally in the energy balance, it's going to be more favorable to have this type of an architecture. So from a control standpoint, I like to tell people, when you look at these integrated products, each one of these is a node on the 1939 CAN bus. So you're getting information, from the point of work. And some of the messaging that we get on the CAN, things like motor current, so you can see for motor current how much torque, and if you have a pressure sensor feeding back on the CAN, you can really start to do hydraulic horsepower versus battery power input, motor RPMs. You can start to think about RMS work, life cycles, all those things. We're also getting data on the motor winding temps and oil temp. So all that stuff is available on the CAN, and we can do a lot of different things with that data to help, predict system health, troubleshoot prognostics. And once again, we get performance from the point of work, not just in a traditional centralized system where we have one inverter, one motor. We actually can see what's going on at the work function. So if we have a problem at one point on the machine, we know exactly where it is. No troubleshooting is really required from that standpoint. Real-time data, so we don't get prognostics off the machine, but we do get good diagnostics. And so, for example, we can tell how much work is actually done, versus power consumed by the battery. So in terms of optimization, we can really optimize the point of work here that we can't do with a centralized system. And lastly, talked a little bit about IoT solutions, but when we have this much data on the bus, we can transmit that live. We can either run it through a machine controller and manipulate the data and get some real findings, or we can generate that to the cloud and then pull that data down so the people actually operating the machines can look at what's going on. I know in some cases we have IoT solutions on our electrified equipment, and we can look at any time and see how much work is being done, how efficient it is theoretically versus actual, and that data will help tell you if there's any degradation in the performance of the device. So, if day one it consumes X power and provides this much work, and then a year later it's starting to diminish, we know that there's a problem with the device, probably has to be replaced in the field. So lastly, some takeaways, and then we'll have some time for Q&A. So from a market need standpoint, what we're trying to do as one of the suppliers in this industry is help develop more efficient fluid power systems that goes through from the motor to the drive, which are typically high efficiency, but any point of efficiency we can get, helps. Fluid power systems, generally reducing losses through hoses, through fittings, slippage through pumps, right? And then again, we talk about all these trade-offs. We need high efficiency pumps that can operate at higher speeds. We've got bent axis pumps today that are amazingly efficient throughout all speed ranges, but then they have a bit of a noise penalty at higher RPMs. And of course, we need to keep things reliable, and if not maintenance free, predictable maintenance, so that we can tell if we promise a 5-year life cycle, for example, the data can point and say, yeah, you're good, or you need to start thinking about replacement. And that's really the power of a lot of these IoT solutions. So once again, from an industry standpoint, one of our focus areas are high-speed, low-noise hydraulic products. And there are a number of different technologies on the table. They all have their pros and cons. There are some endurance requirements and electrification that are actually different and more stringent. For example, we can accelerate a pump at a much higher speed or time to get to RPM than we can with a diesel engine. So that puts stress on the pump, on the housings, you name it. We have to look at total system architecture. We often get so looped up in one part, the valve pressure drops or the hose pressure drops. We have to look at really the whole system. We look at highly integrated products like this at their function as a way to get to better machine design. Once again, you can never forget about the thermal systems, how we cool, how much cooling is required, and not just the hydraulic system, but how that plays into to battery cooling and inverters. Inverters generate a fair amount of heat too. And then lastly, as we move into this, and I know in our own company, we find that we need to be looking a lot more at software and controls from a safety standpoint, reliability, but the whole shift towards digital, from what was historically an analog business in hydraulics, right, is for the industry, it's a pretty big leap, right? We're all trying to figure out where we're going to go with that. So that is the end of the presentation. On behalf of Howard and myself and Fluid Power World, I'd like to thank you for attending. We've got some time for Q&A, so we've got a few minutes open for that.
Great. Thank you so much, Howard and Rich, for such an informative presentation. As Rich mentioned, it's time for the Q&A portion of our presentation. So please submit them to the Q&A box, and we'll get through as many as possible during this session. Any remaining questions, Howard and Rich can reach out to you directly. It looks like we have a few already. So we'll start with, how cost-effective would several integrated ePumps be versus a centralized motor and one larger ePump?
So Howard, I'll take this one, and I'll have you take the next one. So one of the things that we find with integrated ePumps is they do require a certain amount of scale, and there are trade-offs with all designs, right? Typically, where hydraulics excels is we can remove pieces, parts, and replace them without a lot of penalty. We can't do that with an integrated product, right? It is designed for the function. If you need more pressure, more power, you're going to need probably a different product. So that said, and in our conversations with OEs, people who have scale find this very attractive, because once you have scale, you can drive your supply chain cost, your manufacturing cost, high automation. When you get to do that, the cost side of having distributed systems versus centralized becomes favorable. I think if you're trying to do it in small quantity, it's a little tougher, because the price points to get where you need to be require a lot of tooling investments, a lot of automation. So it can be very cost effective, but you do need some volume.
Great. Next question. Why a vane pump? And is that the only option?
Howard, why don't you take that one?
Okay, I'll take this one. Yeah, thank you. The why a vane pump, and is that the only option? No, for sure, it's not the only option. There are other pumps can be bolted on or integrated with motor also. why we use a wind pump, because we mentioned two requirements. One is high efficiency and high speed to match the motor, RPM, and the other one is a low noise. And the wind pump, actually, this is our newly developed or newly improved wind pump technology. They can run much faster than existing gear pump, wind pump, or even piston pump. And we actually leveraging some of our aerospace technology. So this wind pump can run much faster and very efficient. And the other important thing is like a very low noise, because the wind pump is a force balanced. So it meets all those three requirements. That's why we pick a wind pump in this case. But certainly other pumps can be a candidate. Yeah.
Great, thank you. The next question is, what type of machines do you think will go on production first? Smaller or larger machines?
That's a good question. I could answer. Howard, I mean, you've been working with some of the OEs. You see some definite trends. Why don't you comment on that one?
Yeah. Okay. Thank you. That's a very good question. Not only us as a supplier try to figure out, and that question also, I would say, like bothering our customers, OEMs. They are trying to, we all try to figure out, okay, what this thing is going to be applied onto, small machine or large machine. This example we showed is actually for a smaller machine, like a mini construction machine or some utility truck and the work truck, those type of things. I mean, smaller is a horsepower. Smaller is like within 30 kilowatts. So that is considered to be smaller machine or a lower horsepower. But it can also be scaled up to a mid-sized machine. The change will be, you need to change from this low voltage. That's the limit. It's actually not, mostly it's not on the hydraulics, not on the hydraulic pump. It's on the inverter and the motor. Because if we use a bigger pump, then the heat generated from the inverter and the motor just cannot do it. So once you get to a high voltage system, this pump can be scaled up, almost like a ready used for higher power or bigger machine, like a mid-size construction machine. But that one, you need to have a higher voltage system. That's my answer. Go ahead, Rich, you have any?
No, I think, also people ask, we didn't get into power ranges here because obviously there's some scalability, but these tend to be in the 7-15 kilowatt range, a lot of these auxiliary functions, right? So they tend to lend themselves to smaller mid-sized equipment. When you start to get into large systems, right, it gets more complicated to combine components for a lot of different reasons.
Mm-hmm.
Great. Okay, next question is, do you envision an integrated ePump to be a repairable unit for fleets?
Yeah, I'll take that one. That's a really good question. And we were at ConExpo, we had a lot of these conversations with various distributors and OEs. So I've seen a trend. I had an 8-year stint in commercial vehicle and watched products move from the traditional mechanical into mechatronic. We had the same question. It is quite a stretch for fleets who were used to being able to replace a valve, a spring, a poppet in the field to what I would call a mechatronic device, where now you have firmware, you have a lot of critical wiring gaps and control boards connected. Generally speaking, and I asked a lot of people, how would you approach this? And what we find generally is the data produced by the device will help you pinpoint where the problem is. You're going to replace the entire device in the field, and then that product will go back probably to the OE for some form of reconditioning. In other industries, you have reman. In hydraulics, you have a lot of repair house. But I tend to see that model where you're going to order the whole integrated ePump. They're going to swap it out in 20 minutes, depending where it is, right? If it's very deep in or if it's easy to get to. And then that product's going to go back and it's going to be repaired at a controlled site, because there's just too much going on inside from the electrical piece that you really have to know what you're doing to try to service it. It's not just this product, it's really any mechatronic product. And we're seeing more and more of them in all industries.
Yeah, I just try to follow up with the 2 sentences. Like, is it a field repairable? It is, but the field repair, the people need to have both electrical and hydraulic experience, and so you can take that apart and repair it. But this is a modular design. You actually can do that if you know electrical system and also the hydraulic system. And a lot of our existing customer, their field application engineer may not have enough knowledge on that. But we actually try to make that more like field replaceable by identify using the data, actually using the IoT or using data or diagnostic tool to identify what is the issue. Is it an inverter issue? Is it a motor issue? Is it a pump issue? Then we can identify that issue. Then you can take that part off. Yeah.
Okay. We touched on this during the presentation, I believe, but how do you cool these ePumps? Hydraulic oil or water ethylene glycol?
Yeah, Howard, why don't you take the first stab at this one, based on your experience on some of the equipment you've worked on?
Yeah. So for this one, we actually use a hydraulic oil to cool it. And definitely you can use water glycol or other cooling fluid to cool it. But this one, this is really our customer requirement, because the electrified machine, the total machine, they don't have an engine drive a PTO anymore, and they don't have an extra cooling source for us. Say they don't have a cooling fan with the electrical motor. Then that's how we did with the hydraulic oil cooling, and we actually use the same hydraulic oil like a return line to cool it to simplify the system and reduce the cost also. But you certainly can do that with other type of fluid to cool it.
Great, thank you. Next question, what type of data is available, in what format, et cetera, for integrated ePumps?
Yeah, I'll take the first part on some of the data. So typically, on any inverter, so think about what's going on the control board. You've got the power electronics, right? And depending what topology you use and voltage, these are generally low voltage devices. And of course, in electrification, on the other side, we're always talking about super high voltages, right, and getting higher and higher. But these devices, as we have them today, for a lot of reasons, are in the lower voltage range. So, the power electronics are pretty straightforward, but you also have a control board with some I/O assignment and CAN bus. So, in real time, we are measuring, because the inverter itself and the math that it has to do. We're looking at RPM. We're looking at current going into the motor. So with that, you get work. You get, if you want to couple pressure or pressure sensor, right, you can get all kinds of hydraulic horsepower information. We get motor winding temperature. That's something we have to regulate and measure. Feedback on, so remember, there's typically in this device, there's an encoder. So, I mean, we've got motor direction, motor speed. That stuff is available on the can. Oil temp is usually available on the can. So straight data, those are like the main ones. Howard, what else in other formats? I mean, it's usually standard can messaging on the 1939, but did I miss anything?
Yeah, correct. This one actually, we like on the CAN communication, we actually have CAN J1939. That's for really for most of mobile equipment, and also CAN Open if they really want to get into the inverter internal, say, parameter tuning, those kind of thing. We're compatible with the both J1939 and the CAN Open.
Okie doke. I think our last question that we have time for today is, you work around the world. Is this trend global, or do you see some regions pushing more than others?
Yeah, so I'll start off, and then maybe Howard wants to add in. It's a great question. So what's really interesting from our view, right? A lot of our OEs are global and somewhat regional, right? So, you know, when you look at the drivers, there's the electrification driver, and then there's the hydraulic architecture driver, and that really varies. I think, you know, the electrification trend is very much driven by it's global, but also very regional in the United States. It's, you know, state by state very often with the federal government pushing things. Europe is probably ahead of us in a lot of ways. Obviously, Asia is doing a lot of amazing things. So, I mean, from a global standpoint, we are looking at, you know, peer to peer. What I'm seeing is in North America, we're probably on par with our development programs, but I see more adoption in general in Europe in volume, but I would say it's pretty similar. On the integrated ePump concept, for us, it's a low powered solution. That's not low power, it's, you know, 96, 48, 24. So Howard, why don't you finish up with, you know, beyond the electrification side, like the integration, do you see any differences globally, like people wanting to adopt this versus the centralized motor pump system?
Yeah, thank you, Rich. The one big thing, like I would say, like in Europe, the trend is more towards like high efficiency, high speed, low noise, because of their local regulation and emission and sound and noise regulation. So on that part, European is ahead. And there are a number of customers actually requesting our say next generation ePumps or this work function electrification product to comply with their emission regulation and sound regulation. And on that part, the integrated pump will have initially we'll start with a lot more penetration, and that's because this thing not only reduce the cost but reduce the noise, but it's actually much higher efficiency point compared with the conventional centralized system. And yeah, that's Europe. And in Asia actually picking up very quickly. They actually pick up. I saw quite a few Asia OEMs. They start to working on this on this one also. Yeah, so that's just my point. Yeah.
Wonderful. Well, looks like that's all the time we have for today. To the audience, if you have additional questions, you can still enter them in the Q&A box, and our speakers can reach out to you directly. Thank you again for attending this webinar from Fluid Power World. And again, thank you, Dr. Zhang, Rich, and Parker Hannifin for helping bring this great information to our audience. This presentation will be emailed to everyone later today and will also be available on fluidpowerworld.com. Thanks again. Make it a great day, everybody.
Okay. Thank you very much.
Thanks, Rachel.